So I'll briefly remind you of what we've done, and then I'll tell you what we're going to do. So first of all, the references for this lecture, the first part will be based on the second half of this paper, and then I'll discuss some work from this paper, and then I'll go into work in progress with Leo Petrov, also related to some work in this paper. So in the last two lectures, we looked at one system. We looked at QT-SUP and its kind of dual system Q-boson. So QT-SUP was this simple process by which particles, or you can think of it, traffic moves to the right at an exponential waiting time with the rate 1 minus q to the gap, so moderated by the distance. The Q-boson process basically describes the same sort of thing, but it's describing evolutions of gaps. I'm not thinking of the two systems as being coupled in any sort of way. I'm just thinking of them as independent systems. So the Q-boson in one particle jumps to the left at a rate 1 minus q to the height of a stack of particles, and that happens independently at each place. So I showed you a very simple consequence of duality, which was that the time derivative of certain expectations of QT-SUP, which are indexed by states n1 through nk, where you should think of the n1 through nk as encoding the configuration of particles here. It's the labeled configuration of locations, ordered locations. Then this expectations time derivative is equal to the Q-boson generator acting in these n variables applied to the same thing. So then I showed you that for step initial data, we could write down a nice concise formula, which is written here in terms of nested contour integrals and rather simple but illustrative integrand. And then I ultimately showed you how this leads to asymptotics. The question then was posed how to deal with general initial data, and for that matter, how to make this less of a rabbit that I pull out of the hat, and how to actually motivate the existence of such a formula. So for that, I described the beta ansatz. I showed you how Q-boson could be factored into a free evolution equation subject to two-body nearest neighbor label boundary conditions. And from that, I was able to derive for you the following left and consequently right eigenfunctions. I'm not writing down the CQ nu. So these eigenfunctions here I write for general nu, because I'm going to use them for general nu. But the case corresponding to QT-SUP, or Q-boson, is nu equals 0. So there's a slight simplification. I then stated a forward and a candidate inverse transform. Here I've written it in terms of its nested contour integral form, which is most similar to what you see here. And the theorem which I stated, I gave you a brief proof of this second guy when nu equals 0, but I claim that the two hold for nu not equal to 0 as well, was that f and j are mutual inverses on suitable spaces. The proof of this theorem for general nu is contained in a work which I didn't write down. I wrote down yesterday the reference to. It's 1407 8534. Right, sorry, yeah. So that contains the proof of that. Okay. So good. So I'll leave this up there. I'll occasionally refer back to it. So what I'm going to do today is I'm going to move on to a parallel story, or a cousin of QT-SUP, which is perhaps a more well-known process, which is known as the asymmetric simple exclusion process. So the asymmetric simple exclusion process has a history that goes back much further. QT-SUP I introduced with Borodin about 3 or 4 years ago. ASUP, however, goes back to about 1968. So it's a particle system. I'll initially draw it. So my plan for today is that I'm going to first introduce ASAP. I'll tell you some nice things about it, things that are known and then some things that are fairly new. This is a continuous time process on the line. particles jump left and right. And then what I'll do is I will go to a discrete time version of ASAP, which maintains the integrability. It's actually, for those who know, it's related to what's called the 6-vertex model in equilibrium statistical physics. That will put me into the realm of an area that's called quantum integrable systems. And then using that technology, I will go from ASAP and the 6-vertex model, which are both spin 1/2 systems. I'll go to general spin systems, first in the vertical direction, and then by a fusion, I'll go to in the horizontal direction. So I'll explain how all of this works over the course of the talk. Things will get a little bit more complicated later on. OK, so here I'll draw the system, and then I'll describe the system. So just like the Q-boson process, you can either describe the system in terms of labeled particle locations, which I'll do initially, or in terms of occupation variables, which is something that we saw the same sort of discussion in some of Sid's lectures about occupation variables. OK, so I'm going to, just for the sake of sticking with the notation that people have used in the past, I'm going to think of particles as labeled from left to right now. So x1 is the leftmost particle, x2, x3, and so on. I'll assume that there is, let's say, a leftmost particle. Maybe even I'll assume that there's a finite number of particles. And the dynamics for Q-TASAP is that each particle attempts to articulate an independent, asymmetric random walk, continuous time, so jumps to the left at a rate q. So this is not a probability, this is rate q, so according to an exponential waiting time of rate q. And then to the right at rate p. And the only rule is that you can't jump to a site that's occupied. So if you attempt to jump to a site that's occupied, the jump is suppressed, and the clocks are reset, and you continue on. Okay? So you just think, you know, each particle has these little alarm clocks. They ring, they look to see if they can jump, and if they can, they do it, and if they can't, they reset the alarm clock and continue. So for instance, this jump in either direction, these jumps are excluded, these jumps are allowed. Okay? And when a jump occurs, everyone again resets their alarm clocks. For notational purposes, let me fix that. I'll say P is equal. Well, I'm going to just fix that the ratio of P and Q is something I'll call tau. And I'm also going to fix that tau is less than or equal to 1. And what that means is that there is kind of a net drift in this direction. It doesn't really matter for this finite system, but this is what I'm going to do. There's one unfortunate thing, which is that Q here will not play the same role as Q up there. What will play the role of Q is actually tau. Okay? So you just need to accept this. The notation is generally P and Q. They sum up to 1. They're positive, but it's the ratio that really matters. Okay. So there are two different ways of representing this system. So one is what I've written down. This is what I would call in terms of location variables. And here I'm going to restrict myself to K particle sector again. So here I'll define, I'll put a tilde, just meaning that the order of this vial chamber is essentially reversed. And there's also some sort of strict ordering. So maybe I'll put this is going to be the set of all configurations X equal to x1 strictly less than x2. So there is a strict ordering on the particles. This you should see as being different than the state space of the Q-boson process. When I went to the Q-boson process and I wrote down the ordered locations of particles, there you could have arbitrary number of particles in each site, so that you would have weak inequalities on the ordered locations of particles. So here we have strict inequalities, and this is by virtue of the fact that this is what's called a spin 1/2 system. But I'll get into that more later. The other way is in terms of occupation variables, and these would be written as so the space of etas. So etas are supposed to represent eta I, which is for every site I assign a 0 or a 1, or if you choose a -1 and a +1. So 0 means that there's no particle at a site, and 1 means that there is a particle at a site. So in both of these languages, I can describe the evolution of ASAP. Of course, the occupation variables don't require that there be a finite number of particles. They don't really require even knowing how many particles there are. So let me just record for you the generators of ASAP in these two processes, and this will codify what I've just described. So I want to say, let me first give you the particle. So I'll write L part, comma, tau. This will be the particle form generator, so the generator acting on functions of this ordered Weil chamber. So I should think of f as a function from w tilde k to complex numbers. And how does it act? Well, we should be able to just figure it out from this sort of heuristic description I gave. Each particle, right, the rule was that each particle, so I sum over particles I, it jumps to the right at rate I. So a jump to the right means that in the ith coordinate, I increase by 1. Okay, so this just means in the ith coordinate, increase by 1. And so the change in f is the difference between the new value and the old value. And this is occurring at rate p. And simultaneously, I have jumps in the other direction. They occur at rate q. And the effect is that xi is decreased by 1, and everything else stays the same. Now, not every jump can occur, so I need to say that these sums are over I, so the sums are over i's and j's, which are admissible. So what do I mean? Again, I mean it's all over all i's and j's, which lead to terms here which are still in the strict Weil chamber. Okay? Because a jump which is inadmissible doesn't occur. Now, you already see that this is the sum where I sum over all i's and all j's. This is a nice, simple system. This is just the system of non-interacting random walkers. So there is a boundary condition that one will need to impose, and this is how I'll apply the beta ansatz, which takes into account the fact that certain terms are excluded. So in a little while, I'll explain how the beta ansatz works, but it's going to be based on this idea of trying to take into account this boundary condition, or this condition of excluding certain terms in terms of a boundary condition on functions that I want to act on by the free generator. Okay, and the occupation generator, so I'll still write it acting on f, but here this f should be a function from the Weil chamber to, so it's a complex, and here f should be a function from, on this state space, which I haven't written down an expression for, to the complex numbers, let's say. So this is now going to be a function of the etas, and here you can actually write this down in kind of a simpler way. So let's say you sum over all sites in Z, and what you need to do is you need to test. So in terms of occupation variables, the choice is that if you have, let's say, if you look at a particular bond, if you have a 1 here and a 0 here, then you can flip. So that flip occurs if you have a 1 and a 0. So how do you encode that in terms of occupation variables? Well, you write eta y times 1 minus eta y plus 1. So at rate p, this quantity will be equal to 1 only if this is 1 and this is 0. For any other choice of spins, if this is 0 and this is 1, or if this is 1 and this is 1, the whole expression will be 0. So you can also then encode the jumps in the other direction. You say 1 minus eta y plus 1. So these are the two possible things which would cause a jump across that bond, and then the effect of a jump across that bond I'll just write in terms of the same sort of notation that was used in Sid's talk, which is to say I'll take eta and I'll flip y and y plus 1. So this is another way of encoding the process in terms of these occupation variables. Okay. So let me now tell you about the duality between the duality for ASAP. And in fact, I'll state the duality of ASAP as a self-duality, which is something we haven't quite seen. We saw the duality between Q boson and Q T-sap, which is almost a self-duality since the two are quite related. But this is going to be a slightly different form of duality, which I'll unite later on in the talk into a single type. Okay, so let me define a function. And what I want to think of, so in fact, I'm going to first of all describe a self-duality between the occupation process of ASAP and another copy of the occupation process of ASAP. So let's see. Okay. So I'll define G eta mu. So I'll think of each of eta and mu as occupation variables. So these are both occupation variables. So they're just these collections of zeros and ones. Now I need to define this function. So I'll say that G eta mu is equal to tau to the sum I less than equal to j of eta I mu j. And I'll actually define a slightly modified version also, G tilde eta mu, which is the product over all I, eta I mu I, and then the same quantity, this G eta. So the theorem is, and part of this theorem goes back to Schutz. So the duality for G tilde goes back to Günther Schutz. This one is more recent with our work. It says that if I look at the occupation generator with a symmetry parameter tau acting on either G or have you G tilde, then, so this is going to act in the eta variables. Then this is the same as the occupation with essentially what I would call this the space reversal, but it amounts to just inverting tau and P and Q. Right? So if I invert P and Q, then it's like the process is running in the other direction. So it's the same as doing a space reversal, which is going to go on the left, and that's what's going to act in the mu variables. This is going to act in the mu variables. And again, this is for G or G tilde. The proof of this theorem is not as simple as the proof of the duality between Q T-sap and Q boson. So that was a one-liner. This is more involved. One can show it using certain various techniques. One technique is to just explicitly write out the action and follow through, and that's what we do in that first reference up there. But there are other approaches, for instance, in terms of quantum spin chains. I want to give you a simplification of this duality, though. If you assume that the mu, so here's kind of a corollary. So if the mu state, so you should think of the eta state and the mu state as both encoding possibly infinite particle configurations. Of course, if they're kind of infinite in both directions, such a product is zero. So one should be infinite in one direction, perhaps in the other infinite in another direction. But if mu happens to be such that it can be encoded in terms of just k particles, so if mu only has k particles, so then we're going to identify mu in terms of a state x, right? A k particle state x. And now I can rewrite these dualities rather than using mu. I can rewrite them in terms of x's. So for instance, how would I rewrite this sum eta I mu j, sum I less than or equal to j? Well, then I would get g eta x, which would be, say, the product I equals 1 to k of tau to something I'll call nxi of eta, where nx of eta is the sum over all eta y for y less than or equal to x. So in other words, what I do is I count the number of particles in ASAP. So I imagine I have this configuration of ASAP where I have zeros and ones, possibly going far in both directions. I count the number of particles in the eta process to the left of x. Okay? So presumably Well, hopefully that should be a finite number in order for this to really be meaningful. And then for each xi, I count that and I raise tau to that number. And similarly, I can define my g tilde. So it's the same sort of thing, except I additionally include a factor of eta xi times this nx. Now it ends up as I minus 1 eta. Okay. So the duality is still a statement of a similar sort. It says that the occupation with tau acting on g or g tilde in the eta variables is equal to now the particle generator in the reverse process with tau inverse as its ratio of p and q acting in the x variables. So here, this and acting here. Now this is actually useful for computations, which is that if I'm interested, so think of the eta process as the thing I'm interested in. And what this is telling me is that if I now take the expectation of g of eta of x, so I think of x as indexing certain observables of my eta process, of ASAP. So the observables that it indexes are either powers of the number of particles to the left of a given location, or the indicator function that there is a particle at that location, and then powers of this same sort of thing. So what this is telling me is that expectations of observables of that type evolve in the same way as we saw for Q boson Q T-sep according to the evolution equation for the k particle. So if I'm looking at a product of k of these terms, for the k particle ASAP up to space reversal applied to the same expectation. So in other words, if I was just interested in k equals 1 in the evolution of tau to the nx of eta, then its expectation would satisfy just the asymmetric discrete Laplacian p and q. Okay. This is a generalization of the duality that's well known for simple symmetric exclusion process that tells you, in particular, this is the generalization. So if p is equal to q, so tau is equal to 1, this term disappears, and what one is looking at here, g tilde, is just the correlation function. It's the indicator function that eta has particles in positions x1 through xk. And then what duality says there is that the expectation of that set of indicator functions, in other words, the correlation functions for that system, the k-point correlation function evolves according to a k-point version of simple symmetric exclusion process. So this is a powerful consequence, and this will ultimately, in conjunction with the beta ansatz, which I'll briefly describe now, this will allow you to compute expectations of this type. So ultimately, one computes formulas for things like the expectation of tau to the k times nx of eta of t. So you maybe started from eta, from some fixed state eta. So you think, for instance, step initial data here will now, let's say, refer to starting with an infinite number of ones. So every site to the right of the origin is occupied, every site to the left is empty. You run the system, you let stuff trickle to the left, because there's a leftward drift. And you ask the question of how many particles have moved past position x in time t. Well, that's what nx of eta of t records. And this is computing its sort of moments. Well, it's, again, the same sort of idea. It's like q to the thing you're interested in, its moments. So you're computing tau to this quantity, and you're looking at its k moments. Ultimately, we'll get formulas of a similar ilk to the ones which I wrote above. And the terminal direction is that you use those formulas, again, to write down Fredholm determinant formulas and extract asymptotics. And this can be done, but I'm not going to do it. So in that direction, I need to explain to you, rather briefly, how the beta ansatz applies in this setting. And I already made some indications, but I want to fit this into the general class of eigenfunctions, which hopefully are visible above. So the beta ansatz we'll record briefly. So let me define curvy L tau. And before I go there, first of all, this is not a complete triviality what I've said. So I expect some people have questions. I don't know if anyone's willing to ask them. Okay, well, you can ask them at any time. I'm going to define the what I would, in the language of before, call the free generator. This is just where the sum that was present over there, the sum over I and j, the sum is uninhibited. It doesn't exclude any terms. And because of that, I can just do a sum I equals 1 to k of something I'll call the tau Laplacian or the tau discrete derivative or whatever. I'm just going to give you a definition of it in a moment. Acting in the ith variable, so the same idea, acting in the ith variable of u, so where this thing applied to a function of a single variable will be defined as p ux plus 1 plus q ux minus 1 minus ux. Okay, so this guy he's just the generator of a one-dimensional asymmetric PQ continuous time random walk. Okay, so at rate p you jump to the right, at rate q you jump to the left, and this is the difference. This is the original value that you're subtracting off. So here you're just doing independent random walks in each particle. And then I define boundary conditions. And this is an exercise for you to check that these boundary that what I write down after this will hold true. So the boundary conditions which will be necessary to impose on functions such that if they are eigenfunctions of L tau, they will also, subject to boundary conditions, be eigenfunctions for the particle generator, is that if I take the following for any I and evaluate when xi is equal to, let's say, when xi plus 1 is equal, I'll give you a picture, it's equal to xi plus 1 should equal 0. So here's the picture. So here's x1, let's say here's x2. So my vial chamber asks that x1 be less than or equal to x2. So this is supposed to be the region sitting up here, and it's not supposed to include the line. And what this is saying is that if I look at a location which is on the line, so I look at a location for which x2 is equal to x1 plus 1. So what does that mean? So this is, I look at a location which is just above the line. So the line is no longer part of my physical state space. But however, the free evolution equation, it has interactions vertically and horizontally. So it's sending stuff out, and it's supposed to also be taking stuff in from this inadmissible area. And what the boundary condition says is that any function on my state space, the net interaction with the line should be 0. So in other words, what I send out plus what I take in should be equal to 0. So the idea is that you want a boundary condition such that when you look at this component, of course, this guy in the free evolution equation also has interactions with stuff inside of the state space. And the idea should be that this part is, by virtue of the boundary condition, excluded. So again, I leave it to you as an exercise to check that the following is true. So any eigenfunction, so here's a proposition, any eigenfunction for L tau, subject, so satisfying the boundary conditions for all I, restricts on this ordered vial chamber to an eigenfunction for what? For L, the K particle generator. Okay, but now we're in the setup that I described to apply beta ansatz. So we can use beta ansatz as before to compute the left and the right eigenfunctions. And what you get is the following expression. I'll just write down the left one. So it's the same sort of idea. It's the sum over symmetric group, sigma. In fact, the expression which I'll write down is not immediately in the form that one would get from beta ansatz. I've just done a change of variables. I'll tell you in a moment. The reason I've written it under this change of variables is that I'm going to match it to the form that I wrote earlier. So there's these for the left, and then, okay, I'll write the right one as well. The same sort of thing. Of course, this process is kind of moving in the opposite direction, so there'll be a space reversal if you want to completely match it. But actually, these two eigenfunctions are very simply related. It's related just by space reversal, the left and the right eigenfunction. That's because the invariant measures, if you recall, the relationship before was that I needed to apply this, this C, which I didn't write down, but the C is related to the invariant measure for the system, because there was this PT invariant. So this is also PT invariant, except the invariant measures for ASAP are trivial. They are product Bernoulli. And so given that you have k particles, the probability, the term that you get is just a constant. So this explains this reason. The form that you would generally get from beta ansatz actually involves a variable, let's say called xi, which is related to z, like this. And so under that variable, you would get something like xi to the xi or xj's, and then this expression would be replaced by something slightly more general. The eigenvalue, at least in the xi variables, is very simple. So in the xi variables, if I wrote down the eigenvalue, you would well, I'm not going to write down, but anyway, it's very simple to write down. Okay, so how are these related to the Q new ones, which I wrote before? The relationship is simply that I've chosen Q, so the Q up there, not the Q here, Q to equal tau. Right? Here's the Q, or what was the Q, and I've chosen nu to equal 1 over tau. Right? You see, the general form was supposed to be, well, I do a change of variable z to z to minus z to get it in the exact form up there. So the general form was I had 1 minus z over 1 minus nu z, so I should choose nu to be 1 over tau in order to match the form. Okay. There is a little bit of a challenge here, which is that what I explained to you yesterday, or on Tuesday, I assumed that nu and q were both less than 1. This was necessary because the nested contours that I had in my formulas, in particular in the definition of the j in the inversion formula, it was nested, but it needed to be nested in a particular manner so that it included 1. I didn't draw it up there. That it includes 1, but it does not include the other pole, which occurs at nu inverse. So as long as nu is less than 1, the nu inverse is bigger than 1, and you can find nested contours that look like this. So here's 1, here's nu inverse, assuming nu is less than 1, and you get nested contours of this form. Now once you take nu, which is itself bigger than 1, so that nu inverse is inside, then it is a priori impossible to find such nested contours that only include the pole at 1, but don't include the pole at nu inverse. So initially there's a little bit of an impediment. It turns out that there's a nice way of getting around it. In fact, what you do is you take the original formula for nu less than 1, and then you progressively shrink all of the contours to a small contour around 1. Now, as you do that, you cross residues of the prefactor, of the factor za minus zb over za minus qzb. And these residues, I'm not going to go into the details, but these residues organize themselves in terms of strings. So certain specializations of strings. These are actually, for those who know beta ansatz for something like the delta Bose gas, these are the string states that occur in the attractive delta Bose gas. In any case, one gets an expansion into residual subspaces indexed in terms of strings where all of the remaining integrals are over the small contour. Now you're able to analytically, or to deform nu such that nu inverse lies to the left of 1. There's no impediment anymore because all integrals are small circles around 1. And then the final observation, which is very nice, is that when you take nu to now be a power, a negative power of q, actually every string state disappears in the summation that you got. So there's a nice cancellation, and you're left with, again, a rather simple formula for the inversion. So what you get, so just to record the consequence of that for these eigenfunctions, and this is what one then uses to, so the consequence of such a deduction is that if I now define these let's say ASAP, so I define my analog of the forward transform, so this is in terms of the sum over x's in this weakly ordered Weil chamber, or sorry, strictly ordered Weil chamber. So I sum over the right eigenfunctions for ASAP. Then the inversion of this, and this is a consequence of the argument which I just outlined in words, is that the inversion can be written itself as a simple contour integral. So here I was saying to expand around 1, but of course, to relate the eigenfunctions, I did a change of variable z to minus z. So actually, all of my integrals are around -1. So a small circle around -1. So small as to not include minus tau, which was the value of nu inverse. And then you get the same sort of expression that one had before. So Ca minus Cb. Okay, and then the consequence of this f ASA, the consequence is again that these two f and j are mutual inverses. Okay, so even though ASAP is not directly in the realm of the theorems because of this relationship between q and nu, the fact that nu needs to be bigger than 1, we see that by this argument of first shrinking to all these small contours and then analytically continuing in nu, we get an analogous result, which due to the simplification, the fact that all the string states disappear except for this kind of simplest string, we get the analog of before. And so using this in the same manner as we did for Q-TASEP or for Q-boson, we can in conjunction with the duality, we can solve the evolution equations that these sort of tau moments, these tau power moments, satisfy. And I'm not going to labor it by writing down any more formulas, but the point is that I can get formulas of a similar type for the moments I wrote for Q-boson. I get them for ASAP as well. Okay. So what's the question? So, you know, one thing which is nice so far that we've observed is that Q-TASEP or Q-boson and ASAP, they are spectrally cousins. Of course, they're cousins in terms of the fact that they're both perturbations of TASEP. TASEP here would correspond to choosing either P or Q equals 1 and then consequently the other 0. But they are also spectral cousins, meaning that they are descendants of the same parents, the Q-nu parents of the eigenfunctions. They are both special cases. So one is when nu is equal to 0, that's Q-boson, and the other one is when nu is equal to Q inverse. So the question I'll now pose is whether ASAP and Q-TASEP are more than just spectral cousins, but whether they actually can be thought of, you know, they're not just described in terms of their eigenfunctions, they're described in terms of their eigenvalues. And does there exist a single operator, a single transition operator, which degenerates to both ASAP and QT-ASAP, meaning when you take special values of parameters or limits, which recovers the two processes. So what I'm going to devote the remaining portion of my time to is developing that theory and showing you that, in fact, yes, there is, and there's actually a 4-parameter family of discrete time versions of these processes, which is diagonalized by the Q-nu operator, or by the Q-nu eigenfunctions, and which rely on 2 auxiliary parameters, alpha and beta. So in that direction, I'm going to now discuss a discrete time version. I'm going to try to, I don't think I'll be using any large formulas anymore, so you can not worry about more contour integrals for the moment. So I'll talk about a discrete time ASAP, which is something that I'll also call the stochastic 6-vertex model. So this particular model, of course, 6-vertex model goes back to a long time ago, Linus Pauling, and then it was studied in depth by Lieb, who described the beta ansatz for this 6-vertex model, as I'll mention in a moment. The stochastic version of it goes back to Gua and Spohn, to my knowledge, and was recently studied in the manner that I'll describe in the second reference of the archive up there. So what is it? Well, so first of all, it's going to be a discrete time process, and I'll describe it initially in terms of particles, and then I'll describe it in terms of what I would call transfer matrices or R matrices. So let me say I have time 0, and then I have time 1. I want to describe how a configuration of particles, let's say I have a particle here, and a particle here. I have 3 particles. How do I update the configuration of particles from time 0 to time 1? So what I do is it's going to be a sequential update from the left to the right. So I start at the leftmost particle. And that leftmost particle, so here's going to be, this is the time 1. Let me actually make this one also. Okay, so this is a dotted line as well, or a dashed line. Anyway, so what happens is this particle starts going up, and then it decides, do I want to go up and just stay in the same spot, or do I want to move over by 1? Now, there is a parameter, I'll say B1, and with probability B1, the particle just stays put. So B1 should be between 0 and 1. And with probability 1 minus B1, the particle moves to the right by 1. Easy enough, right? Let's say that the particle moves to the right by 1. So it chooses to make this step to the right. Now it continues to move to the right. It continues to move to the right, and it moves to the right now with probability B2. Or it stays put with probability 1 minus B2. So there are 2 things at play. So you should think of it as, do I get out of bed in the morning? And then once I'm out of bed, do I keep walking and keep breathing? So there is a sort of force of friction, you know, your probability of actually starting to do something. And then once you're doing it, your probability of continuing to do it. And so once you've activated yourself, once you've chosen not to stay put, then you continue to move to the right with probability B2. So effectively, you would move to the right according to a geometrically distributed distance with parameter B2, except for the fact that there is a next particle. So, but let's assume that this particle only moves to the right by 2, and then it decides to stay put with probability 1 minus B2, so the new particle's position is here. Now we move to the second particle. So the second particle plays the same game. He says, do I want to stay put or do I want to move? Let's say he moves to the right by 1, and then once he's moved to the right, so this is with probability 1 minus B1, then he moves to the right again, probability B2, moves to the right again, probability B2. But now the particle has bumped into the guy in front of him. All right, here's where the next guy is. So he bumps into him and he says, I'm very sorry, I'll stay put, but I need to occupy this space because there's no turning back. and you need to move forward. So once you encounter a position which is already occupied, you're forced to stay put there, and you force the guy with probability 1 to move 1 to the right. So it's like you activate that guy with probability 1, and then this guy continues along according to the B2 rates. So is this clear? So the only difference between kind of an individual particle just activating and running to the right is that occasionally you'll hit the next guy. You'll be forced to stay put, and he'll be forced to move. And then once he's moving, he continues to use the B2 probabilities. Okay. So this is the model. Now, how is this related to ASAP? Well, let me tell you the degeneration, or the limit of this model, which gives you ASAP. So let me say, imagine that B1 is equal to epsilon Q, and B2 is equal to epsilon P. Epsilon being small. So what does that mean? That means that it's very unlikely that you stay put. Right? You stay put with probability epsilon Q. So it's very likely you'll move by 1. However, once you've moved by 1, it's very unlikely that you'll move again, because you move again with probability epsilon P. So what it will mean is that I'm now going to think of time, so time, as being on the order of epsilon inverse, say, tau. Each particle under this sort of scaling will typically, if I think of this as my time direction, will typically just proceed along a diagonal. Right? Every particle will just move to the right by 1. Except every once in a while, and this will happen according to, under this scaling, a Poissonian event. Every once in a while, a particle will deviate. It'll either decide to stay put, and it will decide to stay put at a Poisson process of rate q, or it will decide to move by 2 to the right. Now, in terms of the moving frame, which, of course, you need to subtract off, what do you see? Well, what you see is that every particle stays put in the moving frame, except with rate q, in the renormalized tau time, it jumps to the left, and with rate p, it jumps to the right by 1. So even though this process was, in a sense, totally asymmetric, the limit under this moving frame becomes asymmetric. And moreover, this interaction, if you think about it for a moment, this one implies the exclusion rule. So this limit recovers in the moving frame ASAP. Okay. Any questions about that limit? There are other interesting limits. For instance, you can take the limit under which only B1 goes to 0. So you fix B2, and you take B1 to 0, and you do the same rescaling of time. And under that limit, you almost never move, but once you move, you do it according to a geometric distribution, except you occasionally will bump the next guy in front of you, and then he'll get activated. So it's almost like frogs on lily pads. You know, they go to sleep. Occasionally, a frog wakes up. It hops a little. If it hits the next frog, it goes to sleep, and the next frog activates. So this is another limit of this model. Okay. Now, here's a proposition. You can see a proof. I'm not going to give it, but the proof effectively goes back to Lieb. There's another proof written in that paper up there, which is that this process, if I think about the k particle restriction of it, this process, this is diagonalized by the same eigenfunctions, by these ASAP eigenfunctions with eigenvalue. So with tau equals to the ratio of B2 and B1, and with explicit eigenvalue, and with eigenvalue, which is of a particular form, which I'm not going to labor. I'm not going to prove this, but let me give you one warning. The warning is that unlike ASAP and unlike the Q-boson system, I do not know, and I don't think it is possible, of a way to solve this by the form of coordinate beta ansatz, which I explained to you. So I don't know of a way of rewriting this system in terms of a free evolution equation subject to only two body boundary conditions. So you do need to take into account higher boundary conditions. However, you can still show that it satisfies the right eigenfunction. So it is certainly necessary, it is certainly sufficient to have that sort of factorization, but it's not necessary. The other thing is that this generalization, this discrete time version, it does satisfy a similar form of duality as ASAP. I'm not going to state that right now, but it will turn out to be a consequence of a more general set of results, which I'll explain a little bit later. Okay, so now I want to leverage our discussion on this discrete time ASAP to bring us into the world of vertex models. So how can discrete time ASAP be understood as a vertex model? And for that matter, what is a vertex model? So a vertex model, it ascribes to, so you have a lattice and you put weights on the edges of the lattice, and to every vertex you assign you put values, numbers on the edges of the lattice, and to every vertex you assign a weight according to the numbers coming in and numbers coming out. So I claim that this model can be represented as a vertex model with the following weights, and I'll explain what I mean according to that over the next few minutes. So here are different vertices and here are different weights. So here I have a vertex which will be, I'll do as dotted lines. This means that nothing comes in and nothing goes out, and I'll say that this has weight 1. Now what do I mean? Well, what I mean is that, I had all of these. I'm just going to fill in with a bunch of dotted lines everywhere that nothing is moving. Okay. And of course, to the left, I have this kind of infinite sea of nothingness. So now, actually, I think at my half-integer times, I think of these points as being my vertices. Okay, so I'm actually going to kind of erase this line and this line, and I'm going to look at the evolution of these particles according to the same rules. So the idea will be that by drawing these empty lines and as well as these full lines, what I can do is I can actually encode the transition probability by looking at every vertex of this horizontal strip and taking the product of all weights of these vertices. Now, every vertex either has no particles coming in and no particles coming out, one particle coming in, one particle coming out, or two particles coming in and two particles coming out. So there is a conservation of particle number coming in versus coming out. And by coming in, I mean coming either from the left horizontal or the bottom vertical, and coming out to the right horizontal or top vertical. So now I've said that I should choose I'm going to choose the weight of an empty, nothing in, nothing out vertex to be 1. Now that's very convenient because if I chose it to be anything bigger than 1, I'd get an infinite product, because there's of course an infinity of those vertices to the left of the leftmost particle. And on the other hand, if I chose it to be less than 1, I would get a weight of 0, because the product of things less than 1 is 0. So I'm forced to choose this to be equal to 1. I've already said that the weight of 1 in, 1 out, or sorry, 2 in, 2 out is also 1. That was the condition that if I bump another particle, I'm forced to stay put and he's forced to move. I defined that the weight of staying put, so particle just staying put, is B1. The weight of a particle moving to the right once it's activated is B2. And consequently, the weight of starting to move is 1 minus B1. Sorry, 1 minus B1. And the weight of stopping to move was 1 minus B2. So is it clear how I go? So I go from the left to the right, and I take the product of all of the vertices that I see at these half-integer times. I have an infinite product of 1s. Then I encounter my first non-trivial vertex, which is of this form. And I choose, or I'm assigning the transition probability. So I see this vertex, and I say, OK, that one has weight 1 minus B1. And now I continue, and I see that I have a vertex of this form. And I say that one has weight B2, so now I take the product of the two. And then I do that again. I see another one of these, take B2. And then I see one of these, and I take a B1, and I go on and so forth. And of course, because this type of vertex, I'm assuming that B1 and B2 are between 0 and 1. Eventually, I'm going to die out, and I'm going to have a finite number of moves to the right. And this gives me my transition probability. Does that make sense? OK. It's important that this makes sense, because everything I say subsequent to this will rely on your understanding of this basic model. OK. So it's convenient to encode these weights as matrix elements, because then I can actually write this in terms of some form of matrix multiplication. So let me define two vector spaces. In fact, I'm not going to really worry about them as vector spaces. I'll just think about them as the span of the two types of incoming and outgoing, well, incoming horizontal, incoming vertical edges. So I'm going to think of this as the span of empty edges and edges with one particle coming in. And H1 I'll think of as the span of empty horizontal edges and full horizontal edges. What do I mean? Well, I mean that, you know, I want to describe this as a certain matrix element. So, you know, I can have either incoming straight dashed line or incoming straight line, and I'm just describing all along all the verticals. I'm going to describe my states in terms of V1 and along horizontals in terms of H1. So I can now write these weights as elements of something I'll call an R matrix, which is just going to be a matrix which maps V1 tensor H1 into itself. What does this tensor thing mean? Well, if I have I have this span and this span, then the span of the tensor product is formed. So this tensor product is given by the span of the tensor product of the basis elements, which in other words would be, if I just draw it pictorially, so this is one element, this is another element, this is another element, this is another element. So I'm thinking of mappings from the left horizontal and the bottom vertical into the same sort of set, where I now think of what I get in the end as being the span of the output things. So the matrix elements then consequently will be identified by these sorts of pictures that I was describing over there, by a pair of something from here and a pair of something here. And for convenience, I'll draw them together. Okay. Another way of identifying the matrix elements, which will actually be more convenient for what will come subsequently, is in terms of I1, J1, I2, J2, where I'm going to think about, I'll just draw a vertex, and I'll say that I have I1 things coming in here, J1 things coming in here, I2 things coming in here, and J2 things coming out here. So rather than needing to deal with these dotted and straight lines, I'll actually just describe, I'll think of this as a 0, and this is a 1, this is a 0, and this is a 1, and then I'll let my i's and my j's take values in the set 0, 1. Okay. Now this will be nice because later on, in just a moment, I'm going to consider where an I and j can take more than the set of 0 and 1 values. Now, there's one last drop of notation I need to provide, which is, you know, here I'm not just looking at a single R matrix, I'm not just looking at a single weight, but rather I'm taking a product of the weights as I move horizontally. So the convenient way to think about that is that so I have R matrices, and to every, so I have my lattice, and I'm going to a given location, let's say location XY, I'm going to describe an R matrix. I'll write brackets around it, xy. And what this will mean is I should take the identity at every other vertex tensored with R in position xy, tensored with the identity everywhere else. In other words, this R bracket xy, it's the operator which takes me from a configuration and it maps my values here into values here. And everywhere else it acts as the identity. So in that language, I'm able to describe the update rule for the discrete time ASAP as taking, let's say, R, this infinite product. So I have an infinite product of R minus, let's say, so starting from the left, R minus 1, 0, 0, 1, R 1, 1, and so on. So I'm just going to fix that I'm at level 1. Okay, so this y height is going to stay the same, but now I take the product of these R matrices starting from left to the right, this infinite product. Okay, this is just another way of saying what I said over there, which is that I start updating from left to right, and I just do it sequentially, taking the output of the previous one in the horizontal and using that as the input for the previous, or for the next one. Okay. Yep. This R is a 4 by 4 matrix. This R is the tensor product of a 4 by 4 matrix with the identity matrix in this whole other larger space. Okay? So, but this product makes sense because I'm restricting myself to the attention to a k-particle sector, in which case the R matrix acts trivially to the left of the first particle and it dies out to the right. Okay? So there is suitable convergence of this product to make sense. Okay. So now I'm going to generalize to higher spin. So let me kill this. Okay, so what I'm describing now is going into this work in progress. Initially this is all kind of classical, but this is based off of this work in progress with Leo Petrov, though in some sense some of it is a reimagination of classical work in quantum integrable systems, though you'll see quantum integral systems generally doesn't deal with stochastic processes, and there is a twist that brings you to the realm of stochastic processes. Because after all, for the standard 6-vertex model, one actually assigns these two a weight which you would write as A. I forget. These two a weight which you'd call B, and these two a weight you would call C. That's the standard 6-vertex model, and this turns out to be related via some form of conjugation of the transfer matrix, but I'm not going to go into detail on that. So let me define now. I'm going to lift up to higher spin systems. So I want to define V super I. This will be a generalization of V1. So V1, I said, was the span of zero particles coming in from below, 1 particle coming in from below. So here I'll think of this as the span of 0 particles, 1 particle, all the way up to capital I particles coming in. It's not going to be so convenient for me to draw lots of parallel lines, but you can think about that as what this is representing. And Hj will be, again, the span of 0, 1 to up to j. So pictorially now my R matrices will go from Vi tensor Hj to Vi tensor Hj. Okay. Where I can now have up to I and up to j values there. We're going to, for the first part of this second part of my talk, we're going to fix that, still that j equals 1. So we're going to only allow, oh, sorry, this is a Hj. This is a Vi. We're only going to allow 1 particle to move to the right per horizontal, but we'll allow an arbitrary number of particles in the vertical direction. And actually, sorry, I need to add a little something to this definition. Let me say that VI is going to be equal to the span 1 through I if I is a positive integer bigger than or equal to 1. And otherwise, if I is not, then I'm actually going to take the span to be infinite. So span of the number is 1 through infinity otherwise. You'll see why this is useful, but the point is that if I is this kind of dimension plus 1 of the vector space, then I'll choose the generators to be 1 through I, and otherwise I'll choose them to be 0, 1, 2, 3 ad infinitum. Okay? So that will correspond to infinite spin system, and I'll define, as I said, Hj likewise is likewise defined. Now I'm going to fix in what follows for the moment. I'm going to fix j equals 1, and I'm going to fix q, two parameters, q and nu, and nu will be fixed such that it's related to I, q to the minus I equals nu. And I'm going to define, and I will define, an R matrix, which I'll denote as R, and I'll put a 1 up here. Sometimes I'll leave it off. This means this is the value of j equals 1. There'll be some auxiliary parameter alpha, and this will, as I said, this will go from VI tensor H1 to VI tensor H1. So again, it will give me a transition from numbers in VI cross numbers in 0, 1 to the same sort of thing, 0, 1, VI. And once I've described to you this R matrix, I can describe to you a stochastic process by the same method of taking products, assuming that R is itself stochastic. I'll come back to this relationship in just a little while. So let me give you the R matrix. So pictorially, this will correspond to having M. So I'm going to think of M as being some number bigger than or equal to 0. And the R matrix elements will be defined for their non-zero values as follows, and for all other values, they will be equal. It'll be equal to 0. So if I have nothing coming in horizontally or vertically, and I have M things coming in from the below and coming out above, then I'll say that my R matrix, I'll drop the superscript 1. I'm going to use this notation of I1, J1, I2, J2. So M1. Okay. So we're going to define the following weights. So this will be equal to, now it'll seem that I'm pulling these out of a hat. Okay. There is a hat. The hat is called algebraic beta ansatz. I'm not going to describe the hat to you, but these come out of the higher representations of the 6-vertex R matrix. Okay. I'll tell you the important properties of them that will follow from algebraic beta ansatz, but I really don't have time sufficient to explain the origin of this. But hopefully it will be interesting enough without that. So the other option, assuming that I have 0 horizontal in and M vertical in, the other option is that one of them goes to the right and the other M minus 1 proceed to stay in the same place. Because only one particle can move horizontally. So this needs to occur with a probability which is complementary to the one above, which I'll just write out. It's alpha 1 minus q to the m over 1 plus alpha. So if you sum the two, you get 1. So it's a stochastic transition. The other case would be to have m in and 1 in, and then I can have m plus 1 out and nothing out. Or I can have m in and m out and 1 in and 1 out. So each of these has the respective weights. Which are given as such. This is where the parameter nu comes in. The 1 plus alpha is just a convenient thing to divide by to make everything normalized to 1. Okay, and all other are I1, J1, I2, J2 equals 0. Okay. So let me make a few observations. First of all, these are matrices, which, as I said, I pull out of a hat for you. Well, the hat is that these are designed to have certain nice properties. In particular, it's going to be designed to be diagonalizable via the eigenfunctions written on the top board. And that, is, again, can be shown directly, or it can be shown from algebraic beta ansatz. So there's a direct proof of that in the third reference up there, up to some twisting. The observations. So one observation is that these R's are stochastic. In other words, if I fix I1, J1 and I sum over I2, J2, then my R alpha, I1, J1, I2, J2 is equal to 1. Moreover, I want them to be non-negative. So the entries are non-negative. Well, there are various ways of choosing alpha and nu, and for that matter q, to make the entries non-negative, but I'll just describe two. So they're non-negative if either q and nu are between 0 and 1 and alpha is positive. Is that clear? Can you see? So just check it. The first one is clearly true. The second one is clearly true. The third one, since nu is less than 1, is clearly true, and the fourth one is clearly true. So this is one case. Another case is that if as before we associate nu with the value q to the minus I, then which we need to. So in this case that nu is less than 1. If we write it as q to the minus I, that means that I needs to be negative. So, but for I being negative, v super I will be the second case. It will be the span of, it'll be generated by 0, 1 through infinity. So that will be an infinite spin case. And what I'm saying is that in that case, my R matrix can transition from any values of m. And you see that this is fine because actually everything makes sense for arbitrary values of m. On the other hand, if nu is equal to q to the minus I, and I choose I to be actually in the other case, so I to be in the integer is bigger than or equal to 1, and q in 0, 1, and alpha suitably negative, so less than q to the minus I, and minus negative q to the minus I, then that means that our VI space is actually equal to the span of the numbers 0 through capital I. And you can check that the weights restricted to m between 0 and I are all positive, or at least non-negative. Moreover, and here's the kicker, you can check that the evolution of the R matrix, or the effect of the R matrix, actually maintains this space VI. In other words, the only way you could get out of that space is either by decreasing m equals 0 to become negative, but that occurs, well, when m equals 0, you get 1 minus 1. So that occurs with probability 0. On the other hand, the other way to get out of 0 through capital I is to go from I to I plus 1. But if m is equal to I and nu is equal to q to the minus I, then you still get 1 minus 1, and you get 0. So this actually, by fiat, puts you into this restricts to this space VI very nicely. And in fact, if you take I equals 1, in other words, spin 1/2, so the spin is equal to I over 2, I equals 1 under some changes of variables recovers these weights. And if you're interested in a spin 1, in other words, I equals 2, discrete time version of ASAP, then just plug in I equals 2 to these weights, and so on and so forth. Okay. Now, here's what I'll claim is special about these weights. So or one thing which is special. So I will define in the same way. I'll define a Markov process acting on a k-particle sector. I'll call the transition matrix for that Markov process, I'll call it B alpha q to the alpha. You'll see, so I'm going to be fixing, as I said, I'm going to fix q and nu, and I'll think of alpha as a parameter. The reason I've written this slightly weird form will become apparent a little later. This will be as the transition matrix given this R1 alpha. Okay, so in other words, it's this same construction by which I start at the leftmost particle, and I use the R matrix to compute the weight of the transition, and then I sequentially move from left to right according to these R matrix weights, and that assigns for me the transition probability of my system. So here's the theorem, which I won't prove to you, but as I said, can be garnered from either algebraic beta ansatz or work of the third archive reference above, is that B alpha Q alpha is diagonalized in the Q nu eigenfunctions with eigenvalues which are rather nice. Okay, and if, for instance, if you took I equals 1 case, you would recover what's written above there as this proposition. No, the one's up on top, the Q nu eigenfunctions. Okay, so let me skip that. So now I want to tell you, so this is the beta ansatz solvability. The other key property that we were looking for in all of these systems is the duality. So let me tell you about the duality, which is something new for these systems. So now I turn to duality. So let me define, so this gives you what? So this transition you can think of as this system. You know, the idea is that I want to think of it like I did the Q boson system. So at every site I can have, well, depending on the value of nu, I can have either an arbitrary positive number of particles, right? Or I can have between 0 and capital I particles. But anyway, I want to describe my state of the system in terms of let's say yi's. So yi's would be the sort of occupation variables that I spoke about before. Okay. So of course, if I equals 1, then these are really just the occupation variables. These are the etas from ASAP, essentially. If I'm in the case of the Q boson model, then these can be arbitrary stacks of particles. Okay. So this gives me a transition matrix which acts on configurations in which there's k particles, and that's valid for any k. I'll define the reversed process. I'll just use the same notation I've been using from before. I'll say B tilde Q alpha, alpha Q alpha is just going to be equal to the space reversed process, which, if you recall this P operator I wrote some time ago, this P is just the thing that takes a function of y's and it takes the function of the reversed, so the y minus I for I and z. So that's just the space reversal. And I'll define one other thing. I'll define a TASAP-like process, or an exclusion. It's not actually a TASAP, but an exclusion-like process. There's a general mapping between these sort of zero-range type processes where you can have particles stacked and TASAP type processes. The mapping is that I consider these as the gaps of a particle system. And if the gaps are of this form, then I get a process in which I have particles, let's say x1, x2. I'll go back to the ordering that I spoke about in the past 2 lectures where I go from left to right. And I want to think of the gaps. So the gaps, here's a gap. The gaps of x should evolve according to the mechanism that I described, according to B alpha Q alpha. So in other words, you know, in terms of the particle system, what it means is I start out, so this is the first gap. This is gap sub 1, and then this is gap sub 2, and so on. So I start off at the first gap, gap 1, and I update it according to those rules. And then based on how much I updated that gap, I update the next gap based on its old value and the change in the value of the previous one, and so on and so forth. So I just use the same R matrix, or essentially the same transition, to update this TASEP type configuration. So it's the same thing as the observation that the gaps of Q TASEP evolve according to the dynamics of Q boson. Okay. So now I've defined the 2 processes, the TASEP-like process and the Q boson-like process, or the zero-range-like process. So let me tell you the duality. And there are 2 dualities. One is a self-duality for the process, and one is a duality between the process and the TASEP-like process. So I'll call this generator acting in these variables, the x1 through x, so on, t alpha, or t to the alpha q alpha. So then here's a theorem coming from this work in progress. I'll define my duality functional as I have in the past, as this product, I equals 0 through n, q to the... This is the same duality functional I wrote down in the very first lecture. Then I have t alpha q alpha. In other words, this is like the generator of Q TASEP applied to H is equal to H, and then the reversed process, the transpose. Here, I'm thinking of these as matrices. So H, you know, this is multiplication on the left acting on the x's, and this is multiplication on the right acting on the y's. This is the same thing as the type of duality I wrote down before. So that's one result. If you think about what this means, it means that if I'm interested, say, in the TASEP-like process, and I take expectations, it tells me that effectively evolving the x process and evolving the y process relative to their respective transition matrices has the same effect on expectations. So in other words, I can compute the expectation of the evolution. So if I start evolving the x process, I find that its discrete time derivative, in other words, its value at time t plus 1, can be written as the application of this b tilde operator to the expectation at the value at time t. So it's the same exact setup as before. It's that if I can diagonalize this b tilde, as I just said I can, then I can compute expectations of the TASEP-like process. So immediately from this duality, I get formulas for moments. You see the formula all the way up on top. All I need to do to change this to this TASEP-like process expectation is to replace the eigenvalue of Q boson, which is t to the, which was e to the tz I 1 minus q all the way up on top, by this eigenvalue to the tth power. So I get the same formula where I just raise this thing to the tth power instead of the term up there. Okay. There's actually another duality. It's a second duality, which is similar, or it degenerates to the ASEP duality, which is, I'll define another thing. It'll be a self-duality, so it's a duality between configurations I'll write as y tilde and y. So the y tilde configuration will be, this is I bigger than j, y I tilde, y I. So I'll act by this b tilde, alpha q alpha, on the left. and on the right I'll act by B. Okay, so in other words, what it's saying is that it's a self-duality with respect to the time reversal, or sorry, the space reversal of the process. That's what the tilde means. And this is the same duality functional that intertwined ASAP with itself. And of course, ASAP is a special continuous time limit of the nu equals Q inverse model, as I've discussed. Okay. So that's the story. So that actually gives us the exact same sort of story for this discrete time model in which I have arbitrary spin in the vertical direction and spin 1/2 in the horizontal direction. Now, it seems that I've come to the end of my time, which is unfortunate, because I want to also explain how you can deal with arbitrary spins in the horizontal direction. So we can either continue for a few more minutes, or I could explain this later informally to people. I'll leave it up to the chair to decide. Yeah, so we could, let's say, for those who are interested, so what time is the tutorial? 4? How about for those who are interested, I'll talk for about half an hour at 4 here and explain what's called the fusion of R matrices, which allows you to go from horizontal spin 1/2 systems to arbitrary horizontal spin systems, and ultimately will allow us to replace the systems with this sort of eigenvalue by systems which have an eigenvalue with an extra parameter beta. And so you get, in the end, you get a 4-parameter family, alpha, beta, and q and nu. And it would seem that these 4-parameter family sits on top of every stochastic particle system which is integrable with respect to what's called UQSL2. In other words, all of the systems which we've studied in the last 15 years or so in the context of KPC universality class fit into this family. And this gives kind of a way of uniting all of them. So I'll explain, for those interested, how fusion works. I'll explain it in a probabilistic manner. So it's usually thought of in terms of fusion of representations, but I'll explain it in terms of Markov function theory. And that's what I'll do. So let me just summarize the course for those who won't be coming this afternoon. So here I've come to some sort of reasonable end. I've come up with a process which you can now, depending on the value of nu, you can recover both ASAP and QTASAP, as well as recover the dualities from them. There is the way you recover ASAP I described. You choose nu to be equal to Q inverse, and then that leads you to this discrete time ASAP, and you take a suitable limit, as described above, in order to recover QTASAP or Q boson. Well, in fact, all one needs to really do is look at the eigenvalue and figure out what you need to do to the eigenvalue to recover the eigenvalue above, and effectively taking something like alpha goes to 0 and then taking t to be very large, you get an exponential coming out of this expression. So we've united these as well as we've united their dualities. We see that there's actually 2 types of dualities. I haven't proved these dualities for you. The proof of them, the proof of the first one is a little involved, not terribly hard, but it goes in the spirit of some earlier work that I've done with Borodin. And the second one follows a little bit easier. The overall purpose of this course was to explain to you how, by leveraging certain algebraic structures, structures which I have indicated but not fully exposed, in particular algebraic beta-ons or Yang-Baxter equation, which is behind, in particular, this sort of theorem, how one leverages this algebraic structure to study certain systems, certain particle systems, which have enhanced solvability. In particular, the enhanced solvability comes in 2 forms. It comes in the form of a duality, as well as in the form of the diagonalizability. These 2 things are distinct. However, as I've shown, all of these integrable or diagonalizable systems can also contain dualities. It's not, however, true that every system with a duality is integrable. Okay, so the two are not entirely overlapping. Given duality and integrability, one can use the Plancherel theory, or this diagonalization, this Fj equals the identity, Jf equals the identity. One can use that, which is an extra input which needs to be proved. It's a statement about completeness of the beta ansatz eigenfunctions. One can use that to diagonalize the expectations, the evolution equations that duality implies for certain expectations, and write down explicit formulas for moments. And from those explicit formulas for moments, using some additional techniques, which I did not go into depth on, one can recover distributional information by various generating functions and ultimately Laplace-type transforms. And these allow you to asymptotically analyze the system. And the whole purpose, drawing back to the beginning, of integrable probability is to not only find systems with concise and exact formulas for expectations of interest, of observables of interest, but also to expose the behavior of large universality classes. The universality class that these models can be shown to fit into is called the Kardar-Parisi-Zhang universality class in particular. They show t to the 1/3 fluctuations for things like the number of particles to cross a line in a given amount of time as time and the line go to infinity. And this allows you to prove such results. Now, the purpose of that is not just to kind of say, okay, I can prove it for model A, B, and C, but the purpose is that we still don't have a very good understanding of such complicated non-equilibrium universality classes. And so by finding additional models, we can both expand and refine our understanding of the nature of this universality class, of what its boundaries are, how to go within it, as well as study new phenomena for different processes. So the higher you go to discrete time processes, the more parameters you input into the system, the more interesting models you can get as various degenerations. So for instance, I mentioned another model, this frog hopping model. There are various other models that arise, and each one of them highlights a new property or a new direction in which one can expand this universality class. Of course, the question of truly proving universality, showing that any small perturbation of the microscopic dynamics does not change the universal long-scale limit, is a very different question. And it's a question which remains almost entirely open at this point and has resisted any techniques. So just like for the classical central limit theorem, de Moivre and Laplace initially studied 0, 1, or -1, +1 random walks. They computed in terms of binomial coefficients, the first instance of the Gaussian distribution. It took about 200 years from then to the first proof of the central limit theorem, for instance, by Lyapunov. So this should be thought of, what I've described, should be thought of as a higher analog of computing binomial coefficients and applying Stirling's formula to take asymptotics. I hope it's not going to be 200 years until this is proved to be universal in the sense of the central limit theorem, but one should be somewhat patient. So thank you very much.
Yes?
So I was thinking, would it be possible to write a continuous version of the Q-Tesa process or any other process and just solve the differential equation, and maybe then you can understand long-time behavior?
So that's a very good question. So there, I can describe very briefly one continuous time limit of Q-Tesap. So if you take Q-Tesap and you take Q getting very close to 1. So what Q controlled is it controlled the length scale on which you stay apart from the guy in front of you. So as Q goes to 1, you become very repulsed by the guy in front of you. He's very smelly or he's very erratic. You stay very far back. So in the limit where Q goes to 1 and time goes to infinity, there is a suitable limit which brings you to a particle system, a continuous space particle system, in which individual particles, so let's say this particle is x1, this particle is x2, x3, so on. Particles evolve according to Brownian motion. So subject to a drift. So particle 2, let's say, is subject, so if we describe dx2, it would be db2, so Brownian motion, plus, or maybe minus, e to the, let's see, x2 minus x1 dt. So if x2, so in fact, in this limit, particles are no longer forced to stay ordered, but in this limit, if x2 exceeds x1 by too much, then this gets very large, and x2 gets a drift backwards. So it's like the particles move around, but you kind of, when you start getting near the guy in front of you or past him, you get slingshotted backwards. So this is a system, this system of equations, I can put in a dxi, which is, I think, exactly what you're asking for. The complexity of solving this is just as complex as solving QT-SAP. Of course, one can put it on a computer in the same way that you can put any of these things on a computer, but finding a closed solution for x 300,000, showing its distribution, is just as hard as computing the distribution of x 300,000 for QT-SAP. If you exponentiate x, which is the same xi, which is the same as going and doing this q to the xi game I played with QT-SAP, then it turns out that this exponentiated thing up to some constant, I'll call this zi, then this zi solves itself a nice differential equation. dzi is equal to a discrete derivative in the I coordinate plus zi dbi of t. So this is what's called the semi-discrete stochastic heat equation. Its moments can be computed. Its moments satisfy closed evolution equations, which are the limits of the Q boson equation, in the same way that these x's are the limits as q go to 1 of the QT-SAP evolution equation. This is called the semi-discrete stochastic heat equation. It also has an interpretation via Feynman-Katz in terms of directed polymer models, various things of this sort, but nothing gets simpler. In fact, things get worse, because the moments of this no longer determine its distribution. It's very easy to see. x1 is a Brownian motion, so if you exponentiate it, you get a log normal random variable whose moments don't determine its distribution. So whereas for this QT-SAP, everything was nice, the moments were all finite, when you go to these limits, actually, though you would hope things get easier, mathematically things get worse. Okay. So it's a nice idea, but it doesn't yield fruit.
Other comments or question? I have a small question, and I mean, one more technical and the other more general. So maybe the technical we can discuss later too. So the continuous time limit for higher spin, will this lead to the Fadayev quantum spin chain?
So if you mean the integrable higher spin XXZ type models, yeah, then in the choices, in this type of choice for nu, if you perform a continuous limit, what you should get is a conjugation of the integrable higher spin XXZ spin chain by a suitable diagonal matrix, which I could describe to you. Because the XXZ, even the XXZ spin 1/2 is not stochastic under the standard representation and requires conjugation. So the relationship between ASAP and XXZ is up to conjugating ASAP by something like tau to the number of particles to the left of position x, or something of that form. But in principle, yes, it should, of course.
And the general question is so about universality classes and their roots. So can one extract the content of all the analysis by saying that the root of the KPZ universality class is to be linked to the algebraic structure of type of SU2 or its deformation, or there is more?
I'm not willing to make a statement as to, in the end, you can ask, is the root to the Gaussian universality class, the central limit theorem, Is that due to binomial coefficients? And I don't think that's an explanation for it. It's certainly within the class, it describes it, but I can't rule out that other underlying quantum groups or anything won't also lead to models in the KP's universality class. And I don't have a suitable description of the KP's universality class, which is based off of these quantum groups, that I can make any sort of claim of that sort. No.
Okay, so we thank Ivan again for his talk.